Mercury is the smallest planet in our solar system. It's also the closest to the Sun. Think of it as a tiny rocky ball racing around our star at incredible speed. It completes a full orbit in just 88 Earth days, so a year on Mercury is actually shorter than 3 of our months. But a day on Mercury is, well, very, very long. It takes about 59 Earth days for Mercury to spin once on its axis. This creates a world of extreme temperatures. The side facing the Sun gets hot enough to melt lead, reaching over 400 degrees Celsius. The side facing away from the Sun is freezing cold, dropping to minus 180 degrees Celsius. It's a truly strange and inhospitable place. This little planet is full of surprises. For a long time, scientists thought Mercury was just a dead, boring rock, a bit like our moon, but closer to the Sun. They expected it to be geologically inactive with not much going on. But when our spacecraft finally got a close look, they found something completely unexpected. Mercury was not dead at all. It had a magnetic field, something you usually find on much larger, more active planets. What exactly is a magnetic field? Think of it like an invisible shield. Earth has a strong magnetic field, generated by its molten iron core. This field extends far out into space, creating a protective bubble called the magnetosphere. It deflects most of the harmful charged particles that stream from the Sun, known as the solar wind. Without this shield, the solar wind would strip away our atmosphere, making life on Earth impossible. When the Mariner 10 spacecraft flew past Mercury in 1974, scientists were not expecting to find a magnetic field. Mercury is tiny, and it spins very slowly. Planetary scientists believed that a planet needed to be large and spinning quickly to generate a global magnetic field. So, the discovery that Mercury had its own magnetic field, although a very weak one, was a huge shock. It was a faint whisper compared to Earth's powerful shield, only about 1% as strong. Its existence suggested that at least part of Mercury's giant iron core must still be molten and churning. But how could it have stayed liquid for so long? Being so close to the Sun might help keep it warm, but our calculations said it should have frozen solid long ago. The weakness of the field was another puzzle. If the core was liquid, why wasn't the field stronger? It was a classic Goldilocks problem. The field was too strong for a dead planet, but too weak for a fully active one. As if a weird, weak, lopsided magnetic field was not enough, Mercury had another secret to reveal. When the Messenger spacecraft mapped its surface in high resolution, it saw something remarkable. The planet's crust was covered in long, winding cliffs. These cliffs, called lobate scarps, can be hundreds of kilometers long and over a kilometer high. They look like giant wrinkles on the surface of the planet. These features are not formed by rivers or wind, because Mercury has no atmosphere to speak of. Instead, they're a sign of something happening on a planetary scale. These cliffs are what geologists call thrust faults. They form when the planet's crust is squeezed together, forcing one part of the crust to push up and over another. The most likely explanation is that the planet is shrinking. Imagine a grape drying out to become a raisin. As the grape loses water, its skin wrinkles. In a similar way, as Mercury's giant iron core cools down over billions of years, it slowly contracts. This cooling and contracting causes the whole planet to get smaller. The solid, rocky crust on the outside has nowhere to go, so it buckles and breaks to accommodate the smaller interior. The lobate scarps are the wrinkles that form on the surface as the planet shrinks. It's a slow but powerful process, shaping the entire face of the planet. To understand why Mercury's magnetic field is so strange, we first need to understand how these fields are normally made. The process that generates a magnetic field is called a planetary dynamo, and it requires a few key ingredients. First, you need a fluid, electrically conductive region deep within the planet. For rocky planets like Earth and Mercury, this means a core of molten metal, primarily iron and nickel. A solid core just will not work. The material needs to be able to flow like a liquid. The second ingredient for a planetary dynamo is a source of energy to stir this liquid core. This motion is usually driven by heat. As the planet's core slowly cools and solidifies from the inside out, it releases heat. This heat causes the hotter, less dense liquid metal to rise, while cooler, denser metal sinks. The final crucial ingredient is planetary rotation. As the planet spins on its axis, it influences the motion of the liquid metal in the core. The planet's rotation organizes the chaotic, boiling motion into large, organized columns of flow. These organized flows of electrically charged metal act like giant electrical currents. And as we know from basic physics, any electrical current generates a magnetic field. When you have massive currents flowing inside a planet, you get a large, stable magnetic field that extends far out into space. This is precisely what we have here on Earth. Our planet is large. It rotates relatively quickly, and it has a hot, churning liquid outer core. This combination gives us our powerful magnetic shield, which is really vital for life. For a very long time, astronomers believed Mercury was a geologically dead world. Based on the Dynamo theory, it just did not seem to have what it takes to generate a magnetic field. First, consider its size. Mercury is the smallest planet in our solar system, even smaller than Jupiter's moon Ganymede. Small planets lose their internal heat much faster than large planets, just like a small cup of coffee cools down quicker than a large pot. Therefore, scientists assumed that Mercury's iron core must have completely cooled and solidified billions of years ago. Then there is Mercury's rotation. The planet spins incredibly slowly. A day on Mercury, from one sunrise to the next, lasts for 176 Earth days. This sluggish rotation was another major strike against the possibility of a magnetic field. The Dynamo theory suggests that rapid rotation is needed to organize the fluid motions in the core effectively. It was like trying to start a generator by turning the crank extremely slowly. You just would not expect it to work. So, when the Mariner 10 spacecraft flew past Mercury for the first time in March 1974, the discovery of a magnetic field was a complete shock. The instruments on board detected a small but definite magnetosphere, a magnetic bubble surrounding the tiny planet. It was a moment that sent planetary scientists scrambling back to their drawing boards. The discovery was truly paradigm-shifting. It proved that our understanding of how planets work was incomplete. In March 2011, after a long and winding journey through the inner solar system, the Messenger spacecraft successfully fired its main engine and slipped into a stable orbit around Mercury. It was a monumental achievement of engineering and navigation. For the first time in history, a human-made object was circling the innermost planet. This was not a fleeting flyby. Messenger was there to stay. One of Messenger's primary goals was to study the magnetic field in unprecedented detail. Its highly elliptical orbit took it from high above the southern hemisphere down to just a few hundred kilometers over the northern hemisphere. This path allowed its sensitive magnetometer to sample the field at a wide range of altitudes and latitudes. Messenger confirmed that Mercury's magnetic field is not only weak, but also strangely lopsided. The magnetic equator is shifted far to the north of the geographic equator. On Earth, our magnetic poles are roughly aligned with our geographic poles. On Mercury, the whole field is pushed northward. This strange offset has dramatic consequences for how the magnetic field interacts with the solar wind. In the north, where the field is stronger and closer to the surface, it provides a reasonably good shield against the incoming charged particles from the sun. But in the south, the field is much weaker and its protective bubble is thinner. This means the southern polar regions of Mercury are much more exposed to the harsh radiation and particle bombardment of the solar wind. This asymmetry could lead to differences in how the surface weathers and evolves in the two hemispheres. The lobate scarps on Mercury are not just random features. They are a geological history book waiting to be read. By studying their characteristics, scientists can piece together the story of the planet's contraction. One of the most important clues is how the scarps interact with other features, especially craters. When we look closely at the images from the Messenger mission, we can see that these massive cliffs often cut right through older, pre-existing craters. This relationship tells us something vital about the timing of these events. It proves that the compression and shrinking happened after the main period of heavy bombardment. By carefully mapping every scarp and measuring its length and height, scientists can build a model of the total stress the crust has undergone. This allows them to estimate just how much the planet has shrunk over time. The calculations based on Mariner 10 data suggested the planet's radius had decreased by about 1 to 2 kilometers. However, the new, more complete data from Messenger showed that the previous estimates were far too low. The latest analysis suggests that Mercury's radius has contracted by as much as 7 kilometers since its formation. This larger value for the planet's contraction actually solved a long-standing problem. Earlier models of how a planet with such a large iron core should cool predicted a much greater amount of shrinking than the old Mariner 10 data suggested. The new, higher value from Messenger's complete map brought the observed evidence much more in line with the theoretical models. The evidence was now overwhelming. Mercury is a planet that has been profoundly shaped by the slow, inexorable cooling and shrinking of its giant metallic heart. For a long time, scientists assumed that most of Mercury's shrinking happened billions of years ago, and that the planet was now mostly geologically quiet. However, the incredibly detailed images from the Messenger mission revealed something that really challenged this view. Among those giant, ancient scarps, the spacecraft actually spotted much smaller, younger-looking fault scarps. These smaller cliffs are usually less than 10 kilometers long and only a few tens of meters high. They're crisp and sharp, which suggests they haven't been eroded by micrometeorite impacts for very long at all. This was, honestly, a blockbuster discovery. The freshness of these small scarps suggests they are geologically very young, maybe forming within the last few 100 million years, or even more recently. Their presence indicates that the thermal contraction of Mercury's core isn't over. The planet is still cooling, still shrinking, and its crust is still breaking, right now. This finding totally transforms our image of Mercury from a static museum piece into a dynamic, active world. The discovery of these young scarps was accompanied by another intriguing finding: evidence of Mercury quakes. The small scarps are often found in clusters, which suggests they're the surface expression of ongoing seismic activity. As the crust compresses and breaks, it would release energy in the form of seismic waves, kind of like earthquakes on our own planet. Mercury is likely a seismically active world, shaking with the tremors of its own contraction. The discovery that Mercury is shrinking provides a powerful, tangible link to the mystery of its strange magnetic field. The two phenomena aren't separate puzzles. They're actually two different symptoms of the same underlying condition. Both the wrinkled surface and the faint magnetic whisper originate from the same place: the slow, steady cooling of the planet's enormous iron core. The shrinking is the external, visible consequence of this cooling as the planet's volume decreases. The magnetic field is the internal, invisible consequence, generated by the churning motion of the molten metal that hasn't yet frozen solid. They're really two sides of the same coin. This connection helps us understand why the magnetic field is so weak. A planet that's shrinking so dramatically must be losing its internal heat to space very efficiently. On Earth, the thick mantle acts like a blanket, insulating our core and keeping the dynamo robust and strong. Mercury's much thinner mantle may not provide as much insulation, allowing the core to cool more rapidly. This rapid cooling could lead to a less vigorous form of convection in the core, resulting in a much weaker magnetic field. So the shrinking, in a way, is evidence of the very process that keeps the dynamo weak. Furthermore, the process of core solidification itself might play a crucial role. As the iron core cools, it's believed to be solidifying from the inside out, forming a solid inner core. This process releases both heat and lighter elements, which helps to stir the remaining liquid outer core and power the dynamo. However, the rapid cooling that causes the intense shrinking might be creating a very specific and maybe even inefficient dynamo. The lopsided nature of the magnetic field might be a clue that this cooling and solidification process isn't happening uniformly. To truly appreciate how strange Mercury is, we really need to look at our own planet first. Earth is the gold standard when it comes to planetary magnetic fields in the inner solar system. Our planet has all the right ingredients for a powerful and stable dynamo. We have a large, iron-rich core, with a solid inner part and a vast, churning liquid outer part. This vigorous convection, organized by Earth's relatively fast 24-hour rotation, creates a strong, stable magnetic field that envelops our world like an invisible force field. It's this shield that makes life on the surface possible. The differences between Earth's and Mercury's magnetic fields are, honestly, pretty stark. Earth's field is about 100 times stronger than Mercury's faint whisper. Our magnetic field is also much more symmetrical. Earth represents the ideal, while Mercury showcases a very different and honestly much harsher evolutionary path for a rocky planet. Stepping back to look at the entire solar system, we see a diverse family of planets, each with its own magnetic personality. Venus has no global magnetic field due to its incredibly slow rotation. Mars represents a planet whose magnetic heartbeat has already stopped. The gas giants have powerful fields generated in completely different ways. In this family portrait, Mercury stands out as a true oddball. It carves its own unique niche, a small, slow-spinning planet that somehow maintains a weak, lopsided, and active magnetic field. Faced with the puzzle of a weak, lopsided magnetic field, scientists needed a new idea. The most elegant and widely discussed explanation to emerge is the thin-shell dynamo hypothesis. This theory proposes that the magnetic field is not generated deep within the core, but in a relatively thin, shallow layer of liquid metal just beneath the planet's solid mantle. This idea radically changes our picture of Mercury's interior. A dynamo operating in a much smaller volume of fluid would naturally produce a less powerful magnetic field than one churning through an entire core. It is like using a small hand mixer instead of a giant industrial one. The energy output is just smaller. Another fascinating and honestly rather poetic theory is the core snow hypothesis. This idea proposes a truly alien process happening deep inside the planet's massive iron core. It suggests that as the molten core cools, iron crystals might begin to form in the cooler regions higher up, near the core mantle boundary. These solid iron particles would then slowly drift or snow down through the liquid outer core towards the center. As the iron flakes solidify and fall, they leave behind a liquid that is enriched in lighter elements such as sulfur. This lighter, sulfur-rich liquid would then be buoyant and would rise, creating powerful convective currents. The thin-shell dynamo and the core snow scenario are currently the two leading contenders in the quest to explain Mercury's mysteries. Scientists use complex computer simulations to model how a planetary core might behave under these different conditions. This debate really highlights the limits of our current knowledge. The key to resolving this debate lies in gathering more and different kinds of data. Each model makes specific predictions that we can try to test with future observations. The story of Mercury is far from over. In fact, we're on the cusp of a new and exciting chapter. The BepiColombo mission, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, is currently making its long and complex journey to the innermost planet. Scheduled to enter orbit in late 2025, BepiColombo consists of two separate orbiters that will study the planet and its magnetic environment in even greater detail than Messenger. With more advanced instruments and a different orbital strategy, it will provide new clues to help us distinguish between these competing theories. What secrets will BepiColombo uncover? Will it confirm one of our existing theories, or will it find something so unexpected that we have to go back to the drawing board entirely? Will we finally understand why Mercury's magnetic field is shrinking and why it is so lopsided? Mercury, the Sun's tiny, weird, and wonderful neighbor, continues to beckon. It reminds us that even in our own solar system, there are new worlds to explore and shocking truths waiting to be discovered. Our journey to Mercury has taken us from the scorching, sun-baked surface down to the very heart of the planet. We've seen a world of extremes and contradictions, a place that really defies easy categorization. Mercury presents us with a series of profound and interconnected mysteries that challenge our fundamental understanding of how planets work. The only certainty is that our understanding of this enigmatic world is about to be transformed once again. The next chapter is about to begin,